Transimpedance amplifiers are a crucial component in electronics, particularly when dealing with low-level current signal. Today I wanted to go over on what they can be used for and how we can configure them and different types of configuration, how you even find the information around them. I've had to use a few recently for some gas sensing capabilities. This is a common application for what you'll see. A more common one when you search up a transimpedance amplifier circuit is with photodiodes and the stuff like that, but I've never worked with one and I've used them in gas sensing applications. So let's get into it. But what is it actually? So at its core, it's just a fancy name for a current to voltage converter, really. So we have our current source here, we have our op amp, and we have our feedback resistor, which also acts as the gain resistor for our device. And these are kind of the main generic parts you'll see within a circuit like this one. Nothing else too much you'll see going about. This is just a standardized circuit. This circuit would probably work with whatever, if you have a current source and you're trying to convert it. This is just a very standard thing. This resistor here is the feedback resistor. You change this, the gain goes higher, and this is the high. This is kind of like the frequency feedback capacitor of the sort. So used in a lot of different applications here, and I just wanted to simulate it and you see how it goes through here. So if we click play on my simulation, we can see I've put a 4.7 nanoamp signal. It's going through here. We get a voltage drop across it, amplification, and we get 475 microvolts. Again, if the gain isn't too much, and usually you would have a 2-step, 3-step sort of gain amplification, then you would put this through to a more readable voltage level. So here we've got it 20 times a gain, or 21 times in that configuration, I suppose, and we've got a gain of nearly 10 millivolts. And again, you would feed it through here to your microcontroller to suitable max out 3.2, 3.3 volts. So this is sort of how you would design one around this kind of angle. Let's take a look at a datasheet or a sensor itself. So this is actually one I've used quite recently, and it's an oxygen sensor. And we're looking through this datasheet and we see, okay, so it has a maximum current normal operation 0.01 amps. So open circuit voltage, I believe 0.9 volts, I'm not too sure. So it seems this is temperature dependent, and you will get a change at the different higher temperatures, I believe, which is standard. You know, we see that across all electronic components and such. And we see here that the output signal in milliamps is derived by measuring the voltage drop across the resistor placed across the center output pin. So we have an anode and cathode here. Value of 100 ohms is suggested. Though primarily key is that we have a range of 0 to 25% oxygen, and that we have a output signal in there of 170 to 230 microamps. So this is something we can test and build. If you look on further, you can do some extra reading. So if we jump onto this application's website, this company, we can see we have a whole lot of things. We have the data sheet, we have some application notes, which I highly recommend read on how these types of sensors work if you're using it for that application. So let's say we're designing for one. We jump into this application note here, and it covers it into great detail from their sensors and a more generic overview onto what this circuit is, a TIA circuit, and how we can actually use it. So give a pretty basic block diagram of what it is. So you've noticed that some electrochemical sensors, they require a bias, which is simply something keeping at a certain voltage range. So it could be 3 millivolts, typically 6 millivolts, could be a negative value. Have your transimpedance amplifier or ADC microprocessor, and we can spit that out into whatever we want. So we go down here, and this was the bias I was talking about that some of them require, and we see that we're given a bunch of different application circuits which we can use and configure for our own liking. It gives us some parameters that we should take into account when selecting the op amp, because that is quite a critical thing. So be sure that our op amp of choice is able to take that, and I wouldn't use a generic LM386, I believe. Is that an audio one? Can't remember, but you get the point of a generic op amp. If it's not rail to rail, for example, you might be cutting yourself in the foot there. But you see some more circuits here, and what we're interested in is the circuit for our application. So contrary to the popular signal which you may seen, which I will show you immediately, so something contrary to belief that I just showed you in multisim, and I'll put on screen again, of our feedback capacitor and our feedback resistor, we see something in this configuration which just seems to be just a standard non-inverting op amp and we're getting our voltage drop across this resistor here. Again, this is something else we can do. So this would also be a TIA circuit of some sort. We are just converting this current spit out into a voltage, and we're amplifying. So see, we can just again here is just some simple low pass filtering and our resistor for measuring the voltage. Simple stuff. But let's jump into multisim and see what's happening. So I've already built it here, and I've put 200 micrograms, if you remember from the rain, for a nice number. And if you click play, this is our value here. Notice we have a negative value, and in reality this would not, well, this is ideal components, so you have to take into account the non-ideal parameters of the components you're using. For example, you can't spit out a negative voltage on an op-amp if you don't have a negative voltage rail, as an example. So I'm just going to put minus to this because I have tested this before and it does spit out a minus value, and in that case you get a positive in return. So understanding how this works is really quite critical in that application and how you would design for one. So I'm going to put up some formulas on screen, and for the formulas that you would make use of really. So just remember that we can configure this TI in different configuration. It's not too much of a surprise when we see something we don't see, and you see the application notes associated. So I have this simple circuit here, and it's a more practical example on how we could use this circuit for our own devices. And it's that, let's say this is our oxygen sensor here, and if we have it too low, we want an LED to go off. So this would be a real life scenario of some inner working of an oxygen sensor in this circuit. In that, for example, if you're in a submarine or you work in a chemical lab and the oxygen levels have dropped, I want the LED or the alarm to go off. So this is running, there's nothing go on, and we have a simple comparator circuit here, and of course these are all ideal values, so you will not get the same thing you'll find when you build this, and you should really try to use proper simulated components using LT Spice, PSpice, or whatever manufacturer spice simulation there is out there. And I'm only using multisim again because I'm just testing a circuit's functionality. Will the concept work? And it's that kind of thing. That's why I use it for these general purposes. But of course, if you're testing real life things, use LT Spice, for example. So I want to move this, and for this was that the oxygen is alright, it's at an okay level, and I've done the calculations to say that 1 volt oxygen is less than 2% or something. I don't know what we need to survive, but if we do that, I didn't do so well in chemistry, so I don't know the answer to that one. So I'm gonna shift this, and you'll see once it hits 1 volt, our LED turns on. So in this real life world example, the oxygen is at a critical level and the alarm has been set, the LED has been set to indicate to people that there is an error, we need to do something about it. And that is just one of the many applications you can do this. Once you've got this voltage out of it, you can do so many things with it, and take readings, measurements, or alarms, and that sort of stuff. So I hope you've gotten a better understanding of how these circuits work and what meant for and not. You can use it in your own designs and have a bit more play around with gas sensing, or just in general. Really, I find it really interesting, useful.